सर हमारे स्कूल में बाइनोमियल थ्योरम शुरू हो गया।
मतलब?
ओ, मैथ्स में।
हाँ हाँ।
फिजिक्स की क्लास ही नहीं हो रही है हमारे स्कूल में तो।
क्या नहीं हो रहा?
फिजिक्स की क्लासें होना बंद हो गई।
अच्छा, क्यों?
वो कुछ एनुअल डे के चक्कर में।
ओके, वेरी गुड यार, बहुत अच्छी बात है। ऑलराइट, सो लेट्स come back to the. So, do you remember what was pure translation? This we've already studied. Pure translation, which is linear motion, right? Pure translation में क्या होता है? You don't have any omega, which is that is no angular velocity is there. The only thing you have is what? Linear velocity. ठीक है? तो एक तो हो गया प्योर ट्रांसलेशन, उसमें कोई एंगुलर वेलोसिटी नहीं होती। एक होती है प्योर रोटेशन। अब हम कॉन्टेक्स्ट जो हमारी डिस्कशन का है, रिजिड बॉडी विच हैज एज वी स्टडीड शेप एंड अ साइज, एंड it can also have a pure rotation, in which case different points will have different linear velocity depending on their distance from the axis, which is the rotation about an axis, the fixed point. So this is your disk, and this is your axis, and the disk is rotating. So it's a solid disk, like a discus throw in sports. So this is your disk lying vertically, and it is having some small thickness. Okay, and this is the axis, and there's a fixed point inside the disk through which this axis is passing, and it is rotating with omega as the angular velocity. So a rotational motion has angular velocity and different points on the disk. For example, if we have a front view of the disk from the axis, you see the different points, they are at different radius, and therefore each one of them will have a different omega, because omega is same, different velocity. So v is equal to omega r. Radius is different for this particle and this particle and this particle, right? So these particles are, supposedly the motion is clockwise. So this particle has a different velocity, this particle has a different velocity, this particle has, depending on the radius. So omega is same because it is covering same angle in the case of pure rotation in the same time.
ओके।
So V is equal to omega r. I think this we have already done in circular motion. V is equal to omega r. So V is not same throughout the rigid body. V is different at different concentric circles. If you draw another concentric circle here, the particles lying on this concentric circle have a different velocity because this concentric circle has a different radius,
ठीक।
right? Pure translation में, because there is no rotation, the question of different V does not arise. So if this is your disk, but it is only moving forward without rotation, like this normal, then each point has the same velocity. Then concentric circle doesn't come. Concentric circle comes only when in case of a rotation. Okay. So let's talk about vector form of V and omega r, for example, very importantly. V is equal to omega r is conventionally known to us, but actually V is a vector. Okay, so we can write it as omega. Okay, so this is called as the vector form of the velocity. The tangential velocity is a cross product, vector product of the omega and r.
ठीक है।
Okay, this is new for you. A vector product is new for you. Okay, so what you can do is, if you have a body which is fixed at a point, which is the point of its So for example, I have a disk, and what I do is I hang the disk at a certain point on the wall. Okay, so this is the wall, and I nail it inside the wall. So this is fixed here. And supposingly I take any point P on the disk. So this is the circle in which it is moving. Okay, so this is the point. Now this will have a centripetal acceleration because it is in a circle. So that acceleration is AC towards the center. So it's radial, it is towards the center and is given by omega square r. So this is your centripetal part, also called as radial acceleration of point P. So this is your point P on the disk. Of the millions of masses it is made up of, this is the one which you worried about right now. And if you also talk about the tangential, so this is not a uniform circle it is traversing. The circle is having non-uniform, which means like a vertical circle. At every point the velocity can vary, and therefore tangentially also there is an acceleration. So if the velocity here was 5, next moment the velocity is maybe 4.9. So there's a constant loss of the tangential velocity, and therefore this body also has a tangential acceleration, which is given by r times alpha. Now alpha is the angular acceleration, and is given by radians per second square. Very similar to circular motion, where you have the body and it is rotating, but it is accelerating angularly. So every 1 second, it is attaining a fixed amount of increase in its angular velocity. So omega final minus omega initial divided by the time gives you alpha of the motion. So that's alpha.
In a rotational motion.
Yes. So this was a circular motion actually we studied, if you remember, right?
Similar here.
About similar, very similar. Only thing is, in a circular motion, it was a point mass here, which was moving. Now you have so many masses, okay, and that makes for a shape and a size. So every particle therefore has both a radial acceleration, and since we are dealing with a non-uniform situation, not a uniform situation, we also have a tangential acceleration. So this body in a circular motion, right now its velocity is omega e, but by the time it reaches the second point, the velocity here is omega final, and this is theta, the distance moved in angular motion, right? This is theta, which is s. So you can rewrite s is equal to ut plus half at square. In angular motion, and the easiest example of an angular motion is circle theta. The angle traversed is omega initial t plus half alpha t square, where alpha is the angular acceleration, analogous to your linear acceleration. So if you notice a body which is rotating, and it obviously is rotating, and therefore it exhibits traits of circular motion. So this, but angular motion rather. So circular motion can be an angular motion. I mean, this body, for example, a pendulum. Okay, it is oscillating, and it is not a circle, yet it has a different angular velocity here and a different angular velocity here. So this particular motion is an angular velocity motion, and definitely it has alpha associated with this, right? So if omega initial, omega final, that t is the time elapsed, so omega, the rotational speed is changing. It's a vertical, some part of vertical circle. If it goes up, it can cover the whole vertical circle. But even the small part of it, which is like a simple harmonic motion angularly expressed. Simple harmonic motion is normally linear. Okay, but this is angular. So it goes here, then it goes here, so it comes back. This also shows alpha. So this also is an example of alpha. It's a circular motion. Pendulum is also an angular motion. And this rotational motion which we are studying, which is associated with the rigid body instead of a point mass bob or a car in a circle, we are studying something similar which is rotating angularly, and because it is rotating in a way that omega does not stay same throughout, which it was in the case of a uniform circle. You can't have an omega final different from omega initial in a uniform circular motion. In a vertical circular motion, you will find omega keeps on varying throughout the circle.
ठीक.
So yeah, the centripetal acceleration of a particle of a rigid body and the tangential acceleration of the particle of the body. So there are two accelerations you're talking about. One you're talking about is a C or A radial, also known as A radial. The second one you're talking about is A tangential. So whenever you see a rigid body motion, you should look at it from this point of view, that maybe this has a centripetal acceleration also, and this also has a tangential acceleration. Tangential acceleration in terms of vector is also written as A tangential direction, can be found using alpha into r. So this is a vector product of alpha, and this is the r, the distance of that particle from the axis. Okay, so this is the tangential. So you can see this formula, this is the product. Okay, this is like multiplication sign. But when I've written it the next time, I have put an arrow. So I'm writing vectorially. So you can get questions in which alpha is given to you in ijk, r is given to you in ijk, and you're expected to find the tangential acceleration of the body. So this is AC, centripetal, always towards the radius. So whatever is the vector of radius is the vector of AC. Okay. Let's talk about simple properties associated with a rigid body. So if you have a rigid body, and can be any shape, but should be definite. And what you do is you take any 2 points, A and B, on top of this. So take A and then take B. Let's take 2 points on them and let's join them. So if this body rotates, you can easily see that this may be the axis through the center, and it is rotating like this, okay, in the same plane, XY plane maybe. So, or whatever plane it is inclined at. If it is inclined, then but it stays within the same plane. Now the distance between A and B never changes. Okay, and if you see the point A and you stand here, okay, so you observe point A from point B. Okay, so you're observing another point. What you will find is that the point A is moving perpendicular to the line joining the AB. So AB is this, and if you make it rotate and connect all the points through which this particular point A appears as seen by the point B on the same plate, you will find that A is appearing to move perpendicular to B, like this. Okay, so it is sorry, on the other side, because the motion is clockwise. Okay, so this was your body, and the body is moving. So you will find that this is the direction. So it will appear to be perpendicular to AB line. Okay, and so if you are standing at B as an observer, and you look at A point on the same, it is rotating, you will find that it is rotating, and to you, you become the center of that circle, and you find that A is moving like this. Okay, so A is moving like this. So because A is actually having because it is a circle which it is traversing, so at any point, A has a V velocity, which is tangential to that circle. So the real circle will be, because A is also, because you are fixed now, you are here, and A is moving in a circle. So A is having a velocity A with respect to B. Okay, the way I write in a relative motion. Okay, so and you can see the because A is tangential, this angle is 90 degree. Okay, so we can say that point A rotates about B. So point A appears to be rotating about the point B. And if you have to find the angular velocity of A with respect to B, it will be given by the velocity of A with respect to B upon L. And this is the in clockwise direction. So if you want to write it in a vector format, omega can also be written in a vector. So A with respect to B is given by VAB and L, and this, if I rotate it like this, that the say this particular cork, if you apply a corkscrew rule, this object will go inside. Okay, so inside means minus k, right? So you can see the velocity of omega. If you make it anti-clockwise, the cork will come out, and therefore the velocity will be positive. So remember, omega is actually a vector, and if you see anti-clockwise motion of omega, say 5 radian per second, okay, you can attach a k with that, depending on anti-clockwise plus k. If it is clockwise, it is minus k. So depending on, so k also is a vector. Omega is also a vector, unlike in our previous thinking where omega just had a magnitude of 5 radian per second, so on and so forth. Okay, so similarly, if you stand at B and you stand at A as an observer and you start looking at B, you will find that B is also rotating with an identical angular velocity. Okay, the point is, we are saying we take 2 points on a rigid body, and then what we start doing is we fix one point and study other, which means we are actually doing relative motion study. Now, moving, we're transferring the velocity. What you will find is that that each point in a rigid body, in a rigid body turns like circular, like we saw. A is turning and has a tangential velocity with respect to B. Similarly, B also has a identical angular velocity and identical linear velocity with respect to A. Conclusion is, if we study relative angular velocity, what we find is that each point in a rigid body is turning relative to the other points of the rigid body with the same angular velocity at a given instance. Okay, so if you have to consider 2 points on a rigid body which is rotating, and you say, what's happening to the 2 points, these points A and B? The answer is, if you take up any rigid body which is rotating, then each point is turning relative to the other point of the rigid body with the same angular, which we know because we have been making this statement that this is a body having an angular velocity. So every particle on that rigid body has a same angular velocity but different linear velocity, right? So if you know any 2 adjacent points, or any 2, not adjacent, but any 2 points on a rigid body, okay, at any instance, you can safely say that they will have equal amount of angular velocity. That they can't have different angular velocities if you're on the same relative, or if you're on the same rigid body. But you can only have different angular velocity relative to a point which is outside of the rigid body. Inside the rigid body, I can do the same derivation here, that I become an observer at point A and notice B. And then when I notice B, velocity of B with respect to A, again the same thing will come. Omega BA is equal to V BA upon L. And I'm going to put K here because now I'm watching B. Okay, B is also moving in the same direction. So minus K. So again, identical. Both are. So We took 2 points on a rigid body. We studied their angular velocities, and we found that the angular velocities of any 2 points on the rigid body is identical. They are not no different at all.
ठीक
ठीक है?
Okay.
What else? Okay, now let's do one thing. Since we know what's a pure translation motion and we have some sense of rotational motion, generally what happens is the word which is used very liberally in this chapter is the word of rolling. Like a bicycle wheel is rolling, ball thrown on the ground rolls. So rolling is used, and a lot of people confuse it with the concept of rotation. But these two are different because rolling as a concept, if you think what exactly is rolling, rolling has two parts to it. So one, of course, is the rotational part of it, which means which whatever rigid body you take up shows rotational characteristic. It also shows up one more characteristic of translation, which means it has both combined in it. So the particles on it are also moving forward and yet are also moving in a circular motion. Like a wheel, it moves forward also, bicycle wheel, and it rotates also around its axis. If you have spokes, for example, these are the spokes. So this is the axis around which the wheel rotate, and all the points also move forward. So the wheel also, so the combination of a rotational motion and a translational motion together, constitutes what is called as a rolling motion together. So in a rolling motion, what changes is that if you have a tangential velocity because of rotation only, it is given by omega r, which we've already studied, and we can write it as omega cross r. It's a vector product of the two. So the velocity is happening because of the rotation of the particle around the axis. So if this is the axis and this is the particle you have taken, it can show you a tangential velocity, which is this, right? And now let's talk about another situation, which is what happens when a body is also rotating about its axis of rotation, which is generally it's, for example, here it's center of mass only, right? Center of mass, and the axis of rotation is passing through the center of mass because we're assuming all the masses are located at the geometrical center of the shape. And now if you want to analyze a point P on the body, now you can say that the velocity of this point P, remember this also is moving forward. So one, of course, it has a V velocity which is linear in nature. Okay, so it can have a linear velocity because it is moving forward, plus it can exhibit the characteristic of a rotational motion also, right? So it has a velocity which is tangential due to, so it has two vectors. This is also moving forward and also is having a tangential velocity. So this is the V tangential and this is the V linear because of the translational motion. So this is coming from translational part and this is coming from the rotational part. Two velocities are there, and if you know the angle between the two, you can easily find the resultant velocity to be v1 square plus v2 square plus 2 v1 v2 cos of theta. You can just write them in this format of law of parallelogram. So you can find the resultant velocity of a body which is rolling at any point of a rigid on a rigid body. And you know that the rotational part is written like this. So the tangential part is omega r. So you can substitute one of the values as omega r, the other value as the linear velocity which is given to you, put it and get the answer. So you will get resultant velocity of the point P due to the rotational motion plus the translational motion. Okay. And similarly, what happens is since you are having a linear motion, so you can also have a linear acceleration. You can have a situation where this particular point accelerates linearly and therefore it may have a linear acceleration due to translation because you're increasing the velocity of the vehicle or your bicycle by applying more, pedaling. So you get a acceleration which is linear, and then because you're now rotating it very fast, your angular speed is increasing by the second, and therefore you also get something like an alpha, which is your angular. So angular acceleration can be converted into linear acceleration using the formula of R alpha. So that rotational acceleration which comes into picture because of that is R alpha, and the linear acceleration is what it is generally. Okay, the linear acceleration is generally tangential in nature, like velocity. It is given by this, and sorry, this is the linear acceleration. So you can again do a linear plus the rotational acceleration coming due to angular acceleration. So you can take under root of a linear in the linear direction, and rotation will contribute another acceleration, which will be this r square alpha square. And you can write 2r alpha al cos of angle between them, again cos theta, the direction. So again you have two accelerations associated with a body which is into rolling, one coming from rotation, the other coming from translation.
Okay.
Not very hard. So rolling motion generally, which is in our course, is for bodies like a sphere, like a disc, like a rod. These are the ones we are going to study actually for the purpose of rolling. Okay, now let's take some examples. For example, what you see in front of you is a sphere. So this is your sphere, and so let's consider the point C, and let's say the velocity of this body where it touches the ground. Okay,
Okay.
it touches the ground is this, and it is rolling. Okay, now let's study what are the velocities at different points. The important points where you study, obviously we have studied general stuff, which is take any point on the rigid body, it has two velocities. Let's study here, center, and at the top. So point touching the ground, center, and also let's study it here at the topmost point. Okay. If you want to write the velocity, you can say I can write it as sum of two velocities, one coming from tangential part and the other coming from the linear part. So which is this, right? The center of mass is moving with v naught, and you can notice if you want to find the resultant velocity, it has two parts to it, the coming from rotation, the other coming
Yeah.
from the linear part. Okay, now see the difference. If I say look at the bottommost point, we are now studying the resultant velocity at 3 points, namely bottom, center, top. Okay, so v resultant, so radius is 0. If you no, I think there is a gap here, right? Yeah, this is the distance of the lowermost point from the center. And if you notice at the center, this particular place here, okay, which is say lowest point L, let me call it lowest point. And if you consider the lowest point, if you're moving in a clockwise direction, your tangential velocity is in this direction. So the tangential component is leftward, but the linear component, which is the translational component here, is in this direction. So at the lowermost point, you see a situation where because of the tangential motion, omega r is leftward. So this is omega r part, and the right part is a linear part. Now, if v resultant is 0, which means omega r becomes equal to v naught at the bottommost point. So A, which is the lowest point I'm studying, the tangential component is leftward and the linear component is towards the right. If these two cancel each other, then the resultant is 0, and therefore omega into r plus v naught is equal to 0. So you get omega r is equal to 0,
Okay, sir.
right? So what does it show? That the bottommost point is at rest. This is what happens in pure rolling. The bottommost point is at rest.
Okay.
We will talk about what is pure word meaning here later, but right now your emphasis is you're studying the resultant motion due to the two types of motions included in rolling, and we have taken a special case where V naught is equal to omega r because V resultant, the point touching the ground on this rigid body, is at rest. So remember, such a case is called as the case of pure rolling. The lowermost point is at rest. Okay, now let's go and study this point. Point number center. So let's go to point number B, located at its center, C. Right? Now, if you talk about C, uh, uh, C point in itself will not show any rotation at all. Okay, the C point will have only a linear component because there is no distance like omega r here. R is 0 from this for a point C. R is 0. It only has a linear part. Linear velocity exists because of the translatory motion. There is no radius available to you. There is no distance available of the point from the center. So r is equal to 0. So the tangential part becomes 0. So the C is moving with a velocity v naught equal to. So C exhibits a pure translational motion. So on a pure rolling, the bottommost point is at rest. Another point, because of the combined effect of translation and rotation, is only showing translational. It has no rotational. Let's go to the next one. And I'm drawing a longer arrow for a particular reason. The reason is the C point, which is the topmost point. Okay, topmost point on this. What happens at the topmost point is also quite interesting. Now it has a distance r, so v is equal to v naught because everything has to have the same velocity coming from the translational part. Plus it has omega r. R is there, omega is there, and v resultant is in the same direction as v naught. So omega r is, because the body is moving in a clockwise direction, is in this direction. So if this is a resultant and I say omega r is equal to, say, equal to v naught, so this will become 2v naught. Omega r is adjusted in a manner that the product becomes equal to v naught. So you will see the resultant velocity of the topmost point is becoming 2v naught. And this whole concept of bottommost point touching the ground and is at rest, the center only showing the characteristic of the linear velocity, and the topmost point showing 2v naught. At the top, it is showing this net velocity. This particular thing is called as pure rolling. I don't need to. You said, no, why do I need to make omega r is equal to v naught? Because I'm teaching a specific type of rolling called as pure rolling, where omega r, it is not necessary for omega r to become equal to v naught, which is the linear part. It can be a separate value. Absolutely, it can. And remember, it's a uh, if you see the clockwise nature, it is negative k. So in reality, you can straight away write it as v naught minus omega r k. V naught is in I direction, for example, okay, and linear direction. So I can write it as omega is k, sorry, r can be another, and I can get a resultant in the same direction as I. Okay, the radius is like this. Omega is inside. These two are perpendicular, and therefore the third side is perpendicular to both of them, which is I. So I can get this also, where I can get to write V naught minus omega r into a vector, okay, I, for example. So this is my resultant velocity at the topmost point. I am putting omega r is equal to v naught and saying magnitude wise they're equal. So the net velocity at the highest point is sum of the two velocities, which is 2v naught. You can just add it. Can you get? So what we studied right now is a sample of rolling, a special case called as the pure rolling. We will come in details of this pure rolling, but let me show you something. Pure rolling is just to, and generally that point where, which is a center point, is the center of mass. That is what we refer to. I'll just show you that. When do you do yoga, you get tired after that?
No.
So you don't? Okay. I feel extreme exhaustion.
कितने घंटे करते हो?
50 minutes.
बस
हाँ कम है.
मतलब ओके डिसेंट है मतलब आपके एज के हिसाब से तो
50 minutes से ज़्यादा करा ही नहीं जाएगा मुझसे.
एज के हिसाब से ठीक है उतना.
Okay. How many minutes do you do?
1 hour 20 minutes.
Oh, no break.
No.
Water break?
हाँ वाटर ब्रेक है.
How many?
अब वन सिप.
अच्छा, पहले पी लो नहीं तो जो पीना है.
हाँ मतलब वैसे भी कर सकते हैं.
Okay, that's hard.
ये आपके एज के हिसाब से ठीक है वैसे भी.
That is really hard, man, too.
बट आप कहते कोई तो मार्शल आर्ट कर रहे थे ना अब तो.
नहीं कर पाऊंगा मैं. I dropped the idea because I called up many places. They said you're late and you cannot do this. We need people who are like 10 to 14 years, maximum 19 years, so that they can take that cardio stamina also. So
19 years आप तो सर 52.
हाँ तो उसने मना कर दिया. फिर बोलता है कि आपको इंजरी हो जाएगी. So don't take this level
योगा
of
में मतलब आप कौन सा वाला कर रहे हो?
mix है. स्ट्रेचिंग, स्ट्रेंथ, थोड़ा बहुत कार्डियो भी करा देते हैं. जंपिंग जैक्स वगैरह जैसे नॉर्मल कन्वेंशनल एक्सरसाइज होती है, समथिंग लाइक दैट
कोई आसन?
करवाते हैं.
कौन सा?
मेनली सूर्य नमस्कार होते हैं, नहीं तो हिप ओपनिंग के बहुत सारे होते हैं.
सूर्य नमस्कार मतलब कौन सा वाला? कितने बार
12,
कितने राउंड्स?
12,
12.
12. नहीं. अराउंड आई थिंक 10 या 15 राउंड्स. दैट्स ऑल. उसके बाद दे स्टॉप. ऑलराइट. So I think we've studied it in the right manner that the velocity is 2v naught. So why do we? So when I say, although we will study this later and it's not very difficult, see pure rolling. When we talk about pure rolling, okay, pure rolling, we are saying that this is the velocity v naught. This is 0, and the velocity is. So you can see the relative velocity of 2v naught with respect to another point on the 2v naught, right? Unlike pure rotation, where the velocity between the two particles remains same with respect to each other. But in the case of rolling, dynamics are a bit different. Just give me 1 second. Okay, back. Sweat problem. Long sitting amounts to sweating. So there is another. So this
कुर्ते
is
की वजह से
pure
हो रहा
rolling.
होगा,
हाँ जी,
कुर्ते की वजह से हो रहा होगा,
क्या हो रहा होगा?
कुर्ते की वजह से।
नहीं नहीं यार, long sitting. Okay, AC is also on, but still. Anyway, what do you do? Okay. So you can have pure rolling, and you can also have motions which are written like in a different manner. They're called as sliding motion. Okay.
राइडिंग।
So yeah, so you can roll and slide. For example, when you put a brake of the cycle, थोड़ा थोड़ा
अच्छा,
रोल करती है और स्लाइड भी करती है रुकते हुए. So that is called as slipping.
स्लिपिंग।
Slipping. And there
अच्छा,
is something called as skidding. I don't know you've heard about it.
और जो हम पानी
Sliding
में
in,
जो पानी में जो हम फिसलते हैं वो भी क्या स्लिपिंग होती है?
yes, होती है. So that motion combined with rotation for a tire, it is now rotating less but sliding more, showing more linear motion, less rotating motion. That type of motion, right? So when we study rolling, we will get into specific cases. Any questions in your mind pertaining to pure rolling? What is rotation? Because this is perhaps a very important topic for JEE mains and
ओके,
difficult to understand. That you took a resultant velocity, then you started applying resultant velocity. You can have a resultant velocity here also. All you need is knowledge of vector, that this is one vector and this is another vector, and how to find the resultant of these two vectors. This is the linear velocity component and this is the tangential component of the velocity. Apply law of parallelogram, find this angle, join this is 90
कल
degree, you
मैंने
can find.
रेजोल्यूशन ऑफ वेक्टर्स की प्रैक्टिस कर ली थी।
ठीक है, याद आ गया होगा,
हाँ,
पहले भी करा हुआ
हाँ,
हमने वो. We've done
मैंने
it.
डेरिवेशन भी कर ली थी साथ साथ में।
हाँ. So it helps you to stay in touch. I've seen a lot of people
बिल्कुल
excelling in
साफ हो गया था,
one or two
बिल्कुल साफ हो
chapters,
गया था।
but as the number of chapters will go up, you will find it bit hard. Okay.
तो रेजोल्यूशन पूरा साफ हो गया था मेरा।
Okay. Good. बढ़िया.
फिर
All right. Let's talk about examples of what we have studied, so that can we apply the concept to what we have just learned. So, for example, pick up a rod. Okay. This is another headache, man. Anyway, बननी नहीं है ये. Let me just draw a rod and say what happens to the rod. Okay, so I'm going to draw this rod. That's your rod. And
दैट्स अ
uh,
पेंसिल।
what is it?
पेंसिल।
Okay. Uh, Assume that. And so this rod is of some length and it is spinning with some angular velocity. Omega is given by 2VL by L. Okay.
ठीक है।
So it is spinning like this. And this is the point B and this is the point A. And you remember it's a rigid body. And what you have to find is the velocity of the end of the rod at A. So this is where it is. So find the velocity of the rod at A. Okay. And this angle is given to be with the horizontal, it is inclined at an angle of 60 degrees. So this is your 60 degree and it is spinning. So you have to find the velocity of the point. And remember this axis around which it is moving, the velocity is V naught, which is the linear. So it is also moving forward. This rod is also moving forward and is also spinning. So it shows, so every particle on it has a linear velocity, which is V naught. And since it is spinning, that particle also has a omega r tangential velocity. You have to find what is the resultant velocity of the point A.
ठीक।
Try. So rigid body, in under the influence of both the motions, has a resultant of two velocities called as the the linear velocity and the velocity because of omega r. You have to find the vector sum of these two.
ठीक।
Give it a shot if you can try. I think fortunately, if you notice, the angle between them is given, but you can still think how the angle can be found out correctly. The angle between omega r and the linear velocity v naught. So point A has a linear velocity, which is same as the v naught, and it also is spinning. Okay, this angle is 60, and whatever is tangential to it. So how will this angle be determined? If you can determine this angle, so this is omega r, because it is spinning at that point. It is spinning and it is also moving forward. So one is you have a tangential velocity on that of that particle. Maybe it's lying at the circumference of that place, omega r, but you need to find the new angle which I've just shown you, this one. How do you determine this angle? With the help of the angle of inclination. So if you draw it like this is 90-degree, I guess, because it is spinning around this, and tangential angle is at right angle to the radial. So this is 90, this is 60, this is 30, and therefore this also will be 30.
Okay. Theta 30 मतलब V naught और omega r के बीच.
So now you know v1 square plus v2 square plus 2v1 v2 cos of. So this theta, which is the angle of inclination, is not the angle between the two vectors. It is different.
ठीक है.
क्वेश्चन समझ में आ गया क्या हो रहा है? एक ही रिजिड बॉडी के ऊपर ए की वेलोसिटी, बी की क्या वेलोसिटी होगी? इफ आई टेल यू बी इज एट राइट एट द सेंटर, रिजल्टेंट वेलोसिटी ऑफ पॉइंट बी, सॉरी बी तो यहां पे था, से सी विच इज एट द सेंटर. So it has no distance from the center of the rod. So omega r component तो होगा ही नहीं इसमें. इस क्वेश्चन के अंदर ओमेगा ऑलरेडी दिया हुआ था बाय द वे इन टर्म्स ऑफ लेंथ, तो आपको ये v2 में ये डालना था. v1 was v naught, so this is v naught square plus 2v naught by l whole square plus 2v naught by l into v naught cos of 60. Sorry, cos of 30 that we've established. If you have to find the resultant velocity of center, how will you find? Omega r होगा नहीं ना फिर वहां पे.
हाँ तो
R
V
is
naught
not there. Omega तो होगा, but into 0 करना पड़ेगा. So this center only has a linear velocity.
V naught
Yes.
and
So on the same rigid body,
B में भी
which is
same angle ही होएगा ना फिर.
हाँ ठीक है, same ही होगा. So on the same rigid body, you have different velocities resultant coming. The linear part is same, but rotation is creating difference between them.
ठीक है.
थोड़ा सा टफ टाइप का टॉपिक है, बट इतना भी नहीं है. अभी तक don't worry about the concept of slipping and sliding. We are not worried about that right now. Okay, we just and just for your understanding, if you notice, simply what we are studying is this. This is the example I started with. Okay, so you can see what's happening. The center is having, so every particle is having this velocity. Okay, and the tangential velocity is this, and this green is the resultant. So, so this green is the resultant. Here, see the resultant. Here, see the cancellation. The bottommost point is at rest. So, we are talking about pure slipping. Look at the behavior of this particle. Tangential velocity omega r is this. The linear velocity is the resultant is this. So every particle on a rigid body has a separate resultant velocity. The topmost point is at double the velocity of the center, and with respect to zero, it is double, obviously. This is at rest. And the earlier question was all based on this only, that find the resultant. Only thing was, instead of giving you a tire or a ring, what I gave you was a rod. That's all. That's the only difference,
ठीक है.
right? So if you see a strange looking shape, you don't have to worry. The concept remains unchanged. No change in that. Still is pretty rolling. Okay. Okay, now let's do one more. Okay, just a animation which I want to show you.
एनिमेशन आपने बनाई है?
मैं कहाँ से बनाऊंगा यार? I don't have any software to make this. I wish I could. I will just share it with you on the chat. Have a look at it. You know how beautifully it is shown.
कौन सा कोई चैनल का है क्या?
No, no. I don't follow any channel. Yeah, look at this. I've sent you a link.
ओ
Have a look at it. This will give you a good perspective on.
बेकार एनिमेशन है, इसको चल ही नहीं रहा.
नहीं, नीचे there is a point. Go below. उसमें एक एनिमेशन रीसेट आएगा.
एनिमेशन रीसेट.
Go below. Go below. Down below.
नो बिलो. मैं सबसे नीचे आ गया, उसमें था नहीं.
रोलिंग मोशन के नीचे एक रोलिंग
एक
करता हुआ दिखा रहे हैं.
एक सर्कल दिख रहा है, इसमें काफी सारे डॉट्स बने हुए हैं.
हाँ, उसी में नीचे लिखा हुआ है
अच्छा.
एनिमेशन. गो एंड क्लिक इट. टिक मार्क आ
It's
जाएगा
rolling.
रीसेट के साथ.
रोलिंग.
हाँ
हाँ तो चला गया है, तो बाय बाय.
हाँ, बाय बाय. यस.
अच्छा, फिर सारा रोल करके.
हाँ ठीक है. बट नाउ गो बिलो
ओके.
एंड यू सी रोलिंग ऑन 2D सरफेस. नीचे और नीचे नीचे चार्ट्स बने हुए. रोलिंग ऑन 2D फ्लैट सरफेसेस.
अच्छा, क्लिक कर दिया एनिमेशन पे.
नाउ सी द पिंक पार्ट.
ओके.
This shows you the rolling.
ठीक है. एनिमेशन में तो वो था, कहते हैं GIF.
हाँ, कह सकते हैं. Now go to the previous animation and click on C velocity, acceleration and path.
C velocity,
And
acceleration.
you can click one by one.
अच्छा, and path.
हाँ.
All और बस ना.
Just one. Look at the acceleration in the center. C's acceleration.
C acceleration, angular acceleration और path.
किसी पे भी click, you can see anything. You can see the center velocity of the center. You can see the velocity of acceleration of the center. You can see the path of the center. If you want to see the body, then go to the body. Just the body. See the angular velocity of the body. See the angular acceleration of the body. Or you can see the path of the body. Look at the shape which is getting created because of this motion. Toroid. Some mathematical shape is getting created. Locus of the point.
Parabola.
No, it's not that. Something else.
Hyperbola.
It is something else. So basically, if you see the point P is traversing this point.
अच्छा
Point
साइन
P
का.
को देखते रहो. It's not even sine. It is something else. The point B is traversing this. In a rolling one point P, just see the P. P को trace करा है इन्होंने पूरा का पूरा. Go to VC. See the velocity. VC का कैसा shape है. When it touches ground, the point P touches the ground. See what happens. ये अब ground पे आ रहा है तुम्हारा.
P
ये
point.
touches the ground. Rest पे आ जाता है. The point P is at rest when it touches the ground.
हाँ ठीक है ठीक है ठीक है.
देखा?
हाँ. That.
Let me see the rotation now. नीचे उसके rotation है. Oh, now it is showing me alpha also. Okay. Omega into R. अच्छा.
बीटा गामा.
V नजर आ रहा है.
ठीक है.
Let me see acceleration AC. See AC.
Okay.
Translation. Point P की. सारा point P पे study करना है. Now go to alpha into RCP. Omega.
RCP. Omega into RCP है ना?
Yes. Alpha. Alpha into. So this is your angular acceleration.
अच्छा alpha into RCP.
तो product नजर आ रहा है at point P. Oh, 0. Look at omega.
वापस ग्राउंड पे आ रहा है.
Omega into R. Centripetal. Okay. Towards the center.
मैं all points कर दूं सारे.
नहीं फिर सारे इकट्ठे देखेंगे. Total acceleration भी आ रही है नीचे. You can do a VP total also if you want to see. I am removing VP total. VP total भी नजर आया. अभी हमने VP total निकाला था.
हाँ आ रहा है.
वो ये VP total में देखो ये नीचे की तरफ चला गया. So you can see the VP total also changes in a rolling. Keeps on changing. And at the lowest most point.
जा रहा है.
हाँ 0 पे आ रहा है.
ग्राउंड पे जाते 0 आ जाता है.
Yes. Pure rolling है. तो vector 0 हो जाता है वो. Longest highest point पे. Look at when P reaches the highest point. The length of VP will suddenly increase.
हाँ जी. अब
ये
देखो
बड़ा मेरा पहुंच रहा है. ये longest हो गया.
ग्राउंड पे पहुंचा. अच्छा अब देखो पैराबोला के सबसे ऊपर गया तो वो आ रहा है.
पैराबोला नहीं है ये. We don't call this parabola.
तो क्या है ये?
कुछ और फिगर है. This is not even cos graph. It is not. There's a maths figure which we.
Manifold. Fiber bundle. Zigzag.
No. There is a name given to it. We don't know. It's taught in engineering. दिमाग से उड़ गया मेरे. I knew the. Anyway. So this sense should be there as to what's happening. Okay. All right. Let's go to one more question on this topic. Okay. Since we have not done anything on acceleration, let's see if we can apply ourselves on. So let's say you have a disk. Okay. Let's take a disk. and let's take some points on top of the disk. So this is 2, this is 1, and you can mark different points, 3. Okay. Now the question is that it's a uniform disk and the radius of the disk is given to be r. That's a radius of the disk which is available to you, and this omega is the angular speed which is given to you, will angular velocity. It is also given that the angular acceleration, so angularly the angular velocity keeps on changing, so it has angular acceleration is equal to alpha. Now the center of mass, which is this, has a linear acceleration of a linear. Okay. You have to find the magnitude of resultant acceleration of this disk at point number 1, 2, and 3, given that it is moving in a direction which is this. So to find the resultant A at 2, 1, and 3. This is the linear acceleration given A. Other parameters which are available are these. Alpha is also known to you. So you should know how to write vectorially uh, acceleration as a product of A. If you have to find, how do you write it vectorially? The angular acceleration and the acceleration which is coming towards a. So one is this linear acceleration. This is straightforward in I, but the angular acceleration is something you have to write in a vector format. Alpha.
Okay.
This is angular acceleration producing its own linear not a linear acceleration, producing its own radial acceleration.
Okay.
We had written that the acceleration associated with angular motion is alpha into r.
Okay.
So we are given alpha? Yes. Are we given r? Yes. Are we given omega? Yes.
Okay.
Manji, you trying? If you can write alpha in vector, the a due to alpha, this one, right? If you can write this as a vector, you get your answer. Easily, you can get it. So what is the direction of r? What is the direction of alpha? Take a cross product and you will be able to find your alpha. So we know so keep this in mind. One is translational motion, which is this, and this alpha is the rotational part. So this is the rotational part of the acceleration. This is the linear. You just need to combine them vectorially and get your answers at different points on the disk. I think this is the tangential part, right? So if you consider a point 2, the tangential acceleration r alpha is here. The tangential acceleration is r cross. And if you consider a point 3, then the tangential acceleration is this. And linear acceleration is this. So resultant of this and this. And here I think it will get added straight away at the point 2. Alpha r plus a linear will together, these two together constitute a resultant acceleration of the body at point 2. If you consider here, alpha r is here, and this is your alpha r, and this is linear acceleration again. Something very similar. It's a resultant after all, nothing more than that. Just writing it in IJK format is required. What is the direction of alpha r is interesting. Have you understood the question, Mr. Shitesh?
Yeah.
No. Just be very careful. If you take this point on a circle, it has a tangential acceleration. समझ में आ गया ये part? Tangential. It
Yes.
also has a centripetal acceleration,
ठीक है.
which is omega square r. The point, और obviously एक इसके पास ये भी है a, तो इसके पास एक linear acceleration है, एक angular motion वाली अल्फा क्रॉस आर वाली टेंजेंशियल एक्सेलरेशन है, और ये लीनियर है राइटवर्ड, ये भी राइटवर्ड है, और एक सेंट्रीपिटल भी है टुवर्ड्स द सेंटर, विच इज ओमेगा स्क्वायर आर. 3 एक्सेलरेशंस है इसके पास, क्योंकि ये अपार्ट फ्रॉम हैविंग एंगुलर मोशन इट आल्सो हैज अ रोटेशनल मोशन. सो अल्फा आर भी है, ओमेगा स्क्वायर आर भी है, और टुवर्ड्स द सेंटर ऑफ द सर्कल भी है सेंट्रीपिटल. सो यू हैव टू एडजस्ट 3. दो तो एक ही डायरेक्शन में, द लीनियर एंड द टेंजेंशियल. सेंट्रीपिटल 90 डिग्री पे उन दोनों के.
ठीक.
So be very careful when you write the vectors. If you get a vectors right, you got it. Now you also need to have a sense of direction of alpha and omega, because I told you omega is a vector. How will you find a which is a combination of both alpha and tangential? कैसे निकालोगे? Tangential is made up of 2 components, alpha r and omega square r at one point. How will you find? How will you find alpha r direction? A, tangential is given by cross product of alpha and r. Unless you know so if you're considering the point 2, what is the direction of radius? This, right? Downward,
हाँ जी.
here. So radius का तो तुम्हें वेक्टर मालूम चल गया, minus j है. But what about the vector of alpha? If you don't know the vector of alpha, how will you find the vector of A? Cross product is I cross j is equal to k, j cross k is equal to I. So write I j k. I cross j, j cross k cross I is equal to j. But you need r का पता चल गया, लेकिन अल्फा का मालूम है वेक्टर फॉर्मेट. What is the direction of alpha?
We don't know.
अल्फा क्लॉकवाइज है, एंटी क्लॉकवाइज है? क्लॉकवाइज.
Clockwise.
ये दिख रहा है ना, ये
हाँ जी,
क्लॉकवाइज.
हाँ जी.
सो
Clockwise.
आई टोल्ड यू, ढक्कन खुल रहा है या ढक्कन बंद हो रहा है से डिसाइड होता है ये. इफ इट इज गोइंग
नहीं,
इनसाइड.
राइट हैंड थंब रूल लगाते हैं.
हाँ लगा.
क्लॉकवाइज है ना,
हाँ ठीक है.
तो क्लॉकवाइज है तो ऊपर की तरफ होगी.
माइनस के.
माइनस के.
यस, क्लॉकवाइज में. थर्ड,
मतलब
तीसरी
ऊपर की
तीसरी
तरफ
में चला गया
डायरेक्शन.
ना, अंदर चला गया ना, राइट हैंड से ऐसे स्क्रू अंदर घुमाया अगर, तो
हाँ.
ढक्कन तो अंदर चला जाएगा ना, बंद हो जाएगा ढक्कन. इट विल गो इनसाइड.
हाँ.
So if it is clockwise, it is minus. If it is anti-clockwise, it is coming out towards you. It is plus k. 3D के अंदर तो k ही है ना, अंदर और बाहर. हमारे फेस की तरफ क्या है?
सर क्लॉकवाइज में एक मिनट जरा. अ,
भाई, anything which is anti-clockwise will come out. Outward towards us is what? Plus k.
नहीं, इनवर्ट जाएगा.
Hold on, hold
एंटी
on.
क्लॉक.
एक मिनट.
सर राइट हैंड.
Okay. ये outward क्या होता है? This
आउटवर्ड
is
यानी कि
this is j. This is I.
यू मीन दिस है ना.
This is plus k.
देखो
This is I. Sorry.
सर, अगर ये इस डायरेक्शन में जा रही है क्या होता है, ये क्लॉकवाइज है कि एंटी क्लॉकवाइज है, नीचे की तरफ.
न्यू जा रहा है ना, j क्रॉस. इन दोनों को देखो ना यार. अल्फा इज
अच्छा.
अल्फा. अल्फा ऐसे अल्फा. अल्फा अगर क्लॉकवाइज है तो अंदर की तरफ जा रहा है, तो अल्फा का अपना वेक्टर जो है वो क्या हो गया? माइनस के, बिकॉज वो खुद अंदर है.
ये क्या होता है वैसे, ये क्लॉकवाइज है कि एंटी क्लॉकवाइज.
क्लॉकवाइज. j टू
क्लॉक.
i.
हाँ जी.
j
ठीक.
क्रॉस i, राइट?
हाँ जी.
एक मिनट दिखा देता हूँ. i j k. i क्रॉस j कितना होता है?
आई क्रॉस जे होता है के
k.
कैप.
तो j क्रॉस i क्या होगा?
ए क्रॉस आई होता है जे कैप.
j क्रॉस i माइनस k होगा.
माइनस.
उल्टा. I cross J you said is K. If I go like this clockwise, I cross J.
अच्छा.
If I do J cross I, it will be minus K. उल्टा.
ठीक है.
पहले तो अल्फा की डायरेक्शन एस्टेब्लिश करने आनी चाहिए. हाउ डू यू एस्टेब्लिश अल्फा? डायरेक्शन ऑफ अल्फा. यू शुड नो द डायरेक्शन ऑफ एंगुलर एक्सेलरेशन.
ठीक है.
क्लॉकवाइज एंटी क्लॉकवाइज की टर्म्स में. एंटी क्लॉकवाइज तो प्लस के.
ठीक है. ठीक है सर.
First, you will have to write everything vectorially for, and you should know also how to write the vector format of omega square r, which is another radial acceleration available to you. when you study rotational kinematics, वो ओमेगा अल्फा वाले क्वेश्चन,
हाँ
अनफॉर्चुनेटली कभी भी ज्यादातर जो क्वेश्चंस होते हैं, देयर इज नो मेंशन ऑफ वेक्टर इन दैट. इट इज रिटन ओमेगा अल्फा, दैट्स ऑल. देयर इज नो मेंशन ऑफ दिस एस्पेक्ट, अल्फा की डायरेक्शन क्या होगी. सो जो डिस्क होती है, रिजिड बॉडी होती है, उसके परपेंडिकुलर होती है डायरेक्शन
हाँ
एंगुलर एक्सेलरेशन की. डिस्क तो ऐसे ही है ना,
हाँ
लेकिन
जी
जो एंगुलर एक्सेलरेशन है वो उसके परपेंडिकुलर है.
ये
डिस्क क्लॉकवाइज है, एंटी क्लॉकवाइज है, लेकिन उसके प्लेन के परपेंडिकुलर है एंगुलर एक्सेलरेशन की डायरेक्शन. घूम ऐसे रहा है, लेकिन एंगुलर एक्सेलरेशन उसके परपेंडिकुलर वेक्टर में है.
ठीक है
So if you have a disk, for example, like this, right? This is your disk. It is rotating like this in an anti-clockwise fashion. The angular and it is angularly accelerating, which means it has increasing omega, but in anti-clockwise direction. Alpha is here, perpendicular to it. So अगर ये disk is located in XY plane, अगर ये disk इस plane में है, इस plane में, मतलब ये plane है मेरा, मान लो ये आई ले लेता हूं मैं और ये जे ले लेता हूं मैं, मेरे आई जे प्लेन है, और मैं इसको अब ऐसे घुमाता हूं एंटी क्लॉकवाइज एंगुलरली, राइट. आई मूव इट एंटी क्लॉकवाइज एंगुलरली, आई विल गेट अ प्लस के टुवर्ड्स मी. दिस इज माई डायरेक्शन ऑफ अल्फा. सो अल्फा इज अल्फा के एक्चुअली.
ओके ठीक है
सो ओमेगा एंड अल्फा बोथ आर परपेंडिकुलर टू द शेप ऑफ द रिजिड बॉडी. जनरली जो रिजिड बॉडी का प्लेन है उसके परपेंडिकुलर है ओमेगा और अल्फा.
और ठीक है
ठीक है, वी विल कंप्लीट दिस टुमारो. आई विल स्पेयर यू टुडे. थोड़ा सा मुश्किल है इतने सारे कॉन्सेप्ट्स को इकट्ठा करना, बट वी विल रिवाइज अगेन द डायरेक्शन ऑफ
ये
अल्फा.
एक और बार एक बार दोबारा से रिवाइज कर लें
हाँ, वी विल डू दिस, क्योंकि थोड़ा सा ना एब्जॉर्ब करने में टाइम लगता है. एक तो प्योर रोलिंग पढ़ ली, आई थिंक वहां में रुक जाना चाहिए था प्योर रोलिंग के ऊपर, बट हमें थोड़ा सा आगे ले गए हम इसको, और थोड़ा सा कॉम्प्लिकेटेड प्रॉब्लम हो गया. सो लेट्स मीट टुमारो अगेन एंड रिवाइज एटलीस्ट द डायरेक्शन ऑफ अल्फा and omega and how to use it to calculate resultant accelerations of different points on a rigid body. Once you get to know कि अल्फा और इसकी डायरेक्शन कैसे लगती है, क्वेश्चंस will become very simple.
ओके सर
ठीक है, see you tomorrow then, and please complete a work power energy assignment.
ठीक
I think you are weak in that. You have not understood the essence of. मैं दोबारा पढ़ाऊंगा पॉजिटिव और नेगेटिव वर्क, कि अर्थ ने कितना काम करा, फिर उसने अर्थ के ऊपर इतना काम करा, वो पॉजिटिव था या नेगेटिव था, वो समझाना जरूरी है. थोड़ा सा, थोड़ा मुझे लगा बेसिक डेफिनेशंस में थोड़ी सी प्रॉब्लम लगी मुझे, बट वी विल रिवाइज दैट. बट डू वर्क पावर एनर्जी, यू हैव लॉट ऑफ गैप्स टू फिल. और पीडीएफ मिल गई है तुम्हें उसकी आंसर शीट की?
हाँ मैं मिल गया आपको भेजता हूँ
हाँ भेज दो यार. लेट्स ओपन इट एंड सी how did you answer and what could be the better way to answer it. You should also know what's the ideal way to answer. Correct way क्या होता है आंसर करने का? कुछ जगह कॉन्सेप्ट वीक है, लेकिन कुछ जगह लिखा लेकिन मार्क्स कट गए. सो विल ओपन इट एंड रिवाइज कि कहाँ पे गलती है.
ठीक
मुझे तुम्हारे बॉन्डिंग की कोई खास चिंता नहीं है, बट आई एम वरीड अबाउट योर फिजिक्स नाउ.
ओके
ठीक है, तो मेरे को वो भेज देना पीडीएफ, और प्लीज स्टार्ट वर्क पावर एनर्जी एंड मार्क what words are not clear to you.
मुझे मेनली डाउट तो सब पोटेंशियल एनर्जी और
ठीक है,
हुक्स लॉ में है.
ठीक है, वी विल डू स्प्रिंग एनर्जी and potential energy both. वो spring is also part of the potential energy.
बाकी मुझे ओवरऑल तो वर्क डन समझ आ गई, पोलेशन समझ आ गई,
हाँ
और पावर, बस
ठीक
ये
है अभी
पोटेंशियल और
ठीक है. So we will revise the potential energy part of it. उसी में gravitation आती है, उसी में spring आता है.
ठीक।
चलो see you tomorrow then.